In this section, we will be discussing relations versus functions. So we're going to start off with what a relation is. A relation is a correspondence between two sets. One set is all of the possible inputs to a relation, and the second set is all of the possible outputs of the relation. So for example, we have states and their number of representatives. So Alaska has 1, Arizona has 9, California has 53, Colorado has 7, Florida has 27, North Dakota has 1. So just saying, if I give you a state, then you can tell me the number of representatives that it has. So we're going to talk about the domain and range. The domain is going to be the set of all of your inputs. So in the case of states and their number of representatives, the domain is going to be all the states because that's the inputs, and our range is going to be all the number of representatives that you can have. Now a function is a special type of relation. A relation is a function only if every element in the domain corresponds to only one element in the range. So if I tell you the input, you have to be able to say the output is this. That's what makes it a function. So dogs have a life expectancy of 11. Ducks have a life expectancy of 10. Kangaroos have a life expectancy of 11. Rabbits have a life expectancy of 7. So if I give you an animal, in this list at least, you can tell me what the life expectancy is. So this is a function. Over here we have people and their phone numbers. If I ask, what is Colleen's phone number? You could say, well, it's this or that. If there is any single input that has more than one output, not a function. So if you have to say, okay, I have Colleen, so her number is either this or that, not a function, that's the end of it. Now mathematically, we have a few different ways we can represent functions. We can look at ordered pairs, so an x and a y value, and then the x's will be our inputs, and the y's will be our outputs. We can talk about functions algebraically, so f of x equals x squared. This function is called f, and the variable is x. That's what that means. We can look at a table of values, which is really similar to a set of ordered pairs. It's just looking at it in a different way. Or we can look graphically, because we can plot ordered pairs, and then if we have a full graph, we can just kind of fill in the blanks. So we're going to start by looking at some tables and seeing if we can find the domain and range, and then determine whether or not it's a function. So our domain is the set of inputs, or our x values. So our domain will be 1, 2, 3, 4, 5. And we put it in curly brackets because this is a set. The domain is the set of all of our inputs. The range is our set of outputs, or all of our y values. We have 1, 4, 9, 16, 25. And we want to know, is y a function of x? If I say, I know what x is, if I give you an x, can you tell me what y is? Well, in this case, yeah. If I tell you x is 1, you're going to tell me y is 1. If I tell you x is 2, you're going to tell me y is 4. I can give you any of these x values, and you'll be able to say, y is this. So yes, y is a function of x. Let's take a look at another table. We're going to do the domain and range, and is it a function? So our domain, the x's we have are 1, 2, 3, -2, and -1. Again, because these are curly brackets, because we're talking about a set, the order of the numbers doesn't matter. Our range is the set of outputs, which are all of our y values, which will be 1, 4, 9, 4 is already on my list, 1's already on my list, and I don't have to write duplicates. So that's our range. Is y a function of x? If I tell you what x is, will you be able to say y is this number? Well, yeah, each x only has one y value. So yeah, this one's going to be a function as well. Here we have another table. Our domain will be 1, 2, 3, -2. 1's already on my list, don't have to write that twice. My range will be 1, 4, 9. 4's already on my list, 2. Is y a function of x? This is where things fail. You'll notice that I have a repeated x value. I have 1. So if I say x is 1, what is y? You're going to have to say it's either 1 or 2. As soon as you have to say or, it is not a function. A way that students like to think about this is if an x gets repeated, then it's not a function. And that's because you would have the same input in 2 different places. But you can see here we have 2 different outputs, which is what makes it not a function. So we've looked at tables. Let's see if we can figure out what this would mean graphically. We want to find the domain and range. So the domain is all of our inputs, all of the x values that we touch. There are points on this graph, but ignore those. We want the entire graph. Well, we have all of the x values between -2 and +2, but these arrows say we keep going. So we're going to keep going off to the left forever in terms of x values, and we're going to go off to the right forever in terms of y value, in terms of x values. So we're going to touch every x value on, or somewhere on the x-axis. It doesn't matter what the y value is, somewhere we will hit every x value. The way we write that is -infinity to +infinity. Because we will touch every single x value eventually because of the arrows. Our range will be the y values that we touch. So we're just looking vertically. It looks like the lowest we're ever going to go is this point right at the origin. That has a y value of 0. And then we're going to go up forever. So our range will be 0 to infinity. That 0 has a closed circle on it, so we will have a square bracket. So now we're going to discuss the vertical line test, and that's going to tell us whether our graph is or is not a function. So if any vertical line would intersect the graph in more than one place, the graph does not represent a function. If no vertical line intersects the graph in more than one place, the graph does represent a function. So if we take a look at that graph we were just looking at, is it a function? I need to be able to draw vertical lines anywhere and intersect the graph either once or 0 times. If I intersect it twice with the same vertical line, then it's not a function. But no matter where I put that vertical line, I'm only going to touch the graph once. And that means yes, this is a function. The reason this vertical line test works is because if 2 points hit the vertical line, then they have the same x value or the same input, but they have to have a different output. And that's the definition of what makes something not a function, is if there is a place where the same input gives 2 different outputs, or more than 2. So here we have what's known as a piecewise graph, because it's in pieces. We want to find the domain and range, and then determine whether or not this is a function. Starting with the domain, that's going to be our x values. What x values do we touch? Well, this arrow says we're going to keep going on forever, and that's aimed towards the left. So from -infinity up until we have x values, we have x values, we have x values, we have x values. We hit 1, and it looks like we stop. So we have our domain going up to 1, but wait, we have another piece up here. As soon as we pass the x value of 1, we jump up here. So the x value of 1 occurs here, and all the values between 1 and 2 happen up here. We get all the way to 2, and then just after 2, we jump to this piece. So although the graph is in pieces, every single x value is going to be touched. If it's 1 or less, it'll be here. If it is greater than 1 but less than or equal to 2, it lands here. And if it's greater than 2, we land. So every x value is going to get touched. It doesn't matter what piece of the graph touches it, as long as something does. Again, the range is going to be the y values that we touch. So it looks like the lowest we ever go is right here at the origin. Because I don't see an open circle, it's going to assume to be a closed circle. So that's a y value of 0. And it doesn't look like we have any y values between 1 and 2. Just kidding, they are over here. I don't care what piece of the graph touches it, as long as something does. From 0 all the way up forever, we will be touching y values. So we can go from 0 to infinity. We want to know, is this graph a function? If I take a vertical line and put it anywhere on this function, will it ever intersect more than once? I'm going to use kind of the edge of my ruler to see. And no, I'm only hitting once, only hitting once, only hitting once. Uh-oh. When we hit x equals 1, are we touching the graph twice? We're definitely touching it here because there's a closed circle, but up here, it's an open circle. So there's not actually a point there. That just says we're getting so close to it that you couldn't be able to tell, but there's not a point up here. It's only down here. So we're not intersecting twice. Going on, we're on the line, we're on the line, we're on the line. Uh-oh. At x equals 2, we hit the same problem. We have a point up here. We don't down here. So this is still a function because we're only intersecting once in the upper part. And then we continue on, and that's okay. So yes, this is a function. For it to not be a function, I could fill in either of these circles, and then the vertical line passing through there would hit it twice. But because those circles are open, it is a function. Here's another graph to look at. We want to find the domain, the range, and is it a function? So domain is our x values. How far left do we go? It looks like we don't go any farther left than -1. And that has a closed circle on it, so that will be a bracket. How far to the right do we go? It looks like we stop here at an x value of 3. And that one's an open circle, so we'll use parentheses. The range is our y values, so how low do we go? That's a y value of -5, and it's an open circle, so we have parentheses. Range is y value, so how high do we go? We go all the way up to a y value of 4. And because I don't see an open circle, we're going to assume there is a closed circle there. So our range will be -5 to 4. Is this one a function? Is there any place I can place a vertical line and it intersects the graph more than once? Nope. So that would make this one a function. So yeah, that one's a function. Next up, we have an ellipse, kind of oval shaped. So the domain, what x values do we touch? Looks like we go from -3 up to +5. And because I don't see open circles, we're going to have brackets. Our range, or our y values, we go from 0 to +5. Again, I don't see any open circles. Oh, sorry, +4. I don't see any open circles, so we're going to assume we touch them. Is this one a function? Now this is a beautiful example of not a function, because there are lots of places I can draw a vertical line and I'm intersecting it more than once. Even if only one vertical line exists that goes through the graph more than once, not a function. All right. So we're going to assume there are arrows on the end of this one. Kind of looks like there should be. Our domain, the x values that we touch, clearly we're going to the left forever, clearly we're going to the right forever. So our domain is -infinity to +infinity. Our range, it looks like we're coming down and we're going to keep going down forever, and then kind of looks like we're going up forever. Even though it's slow, we are going up forever, so eventually we'll hit all the y values. So our range will be -infinity to +infinity. So is this one a function? My vertical lines only hit it once. But if I go through here or here, then I'm going to hit it 1, 2, 3 times. Because there exists at least one vertical line that intersects the graph more than once, no, this one is not a function. All right, so we've been looking at graphs. Let's see if we can start doing stuff with them. So we're going to start by evaluating a function. This is very similar to plugging into equations, but at the moment we're going to do it kind of graphically. So it is f of -1. So the -1 has replaced the x. So they're saying if x is -1, what is the function value or the y value? Well, when x is -1, y is 1. So f of -1 is equal to +1. The x value, the y value. What is f of +1? Well, if we look at +1, the y value is 2. This last question is different than the previous two. It says, what is x when f of x equals 0? We are looking for an x value. They're telling us the function value, or the y value, is 0. So what is the x value? So I need to find where on my graph the y value is 0. That happens right here at an x value of 3. So the x value of 3 makes that true. So f of 3 is equal to 0. That's how we would write the full statement. Now that we've done it graphically, let's evaluate functions algebraically. We do this just like we would plugging into an equation. The value of a function is the output of the function. Outputs are typically y values when we graph functions, and the function representation for the output, or y, is f of x. So f of x is just a fancy way of saying y. And the use of it is we can talk about multiple equations at once if we use function notation, because we can name each of the equations something different. So we might have f of x and g of x and h of x. That way we can talk about multiple equations without saying y equals this and y equals that and y equals this. All right. So we want to know if f of x is equal to x squared minus 1, what is f of 3? So we're plugging in 3 for x because the 3 took the place of x. So if I plug in 3 for x, I'm going to make sure to plug it in parentheses. So we have 3 squared minus 1, which is 9 minus 1, which is 8. So f of 3 is equal to 8. What is f of negative 2? Well, that'll be negative 2 squared minus 1. Negative 2 squared is a positive 4, and 4 minus 1 is 3. We would say f of negative 2 is equal to 3. Then we want to know what is x when f of x equals 8. So this one's different than the last two. We're trying to find x when f of x equals 8. So I need to plug in 8 where f of x is. So that would be 8 is equal to x squared minus 1. I want to solve for x, so I'll add 1 to both sides. We'll have 9 equals x squared. To get the x alone, I'm going to take the square root of both sides. But if you ever take the square root of both sides of an equation, put a plus or minus sign on the side without the variable. You will get x is equal to plus or minus the square root of minus 3. So x is equal to either a positive 3 or a negative 3. All right, so now that we have this function notation, we can talk about taking somewhat simple graphs and transforming them into something more complicated by using small changes. So we're going to start with what's called a vertical shift. If you know the graph of a function, it can be easy to graph a similar function using transformations. So adding to a function moves the graph up. So if we have a function f of x equals 2x plus 2, then f of x plus 3, notice that this plus 3 is not inside with the x, it's out back, is going to be the 2x plus 2 that we had plus 3, which gives us 2x plus 5. So what it does is it takes our original line and moves it up 3 units. So if we just add 3 to the end of a function, it moves the entire graph up 3 units. As you can probably imagine, if adding on the end moved the function up, then subtracting from the end, f of x minus 1, is going to move the whole graph down. So if we have our original graph as the darker top one, then if we subtract 1 from the end, that's going to move the whole graph down 1. We can also move the graph left and right. This is going to happen by adding or subtracting inside the parentheses, so it's attached directly to the x. So the way I remember this personally is if we are adding or subtracting to x, we're going to move in the x direction. If we're not attached directly to the x, because we had the subtraction and before the addition out back, then I think of it as attached to the y and we move in the y direction. So if we replace the x with x plus 3, then we get our new equation. The thing is, adding 3 to the x doesn't move it in the positive x direction, it moves it in the negative x direction. So this actually moves it to the left 3 units. And then as you can probably imagine, if we subtract from the x, so if we do x minus 4, that's going to move us to the right. So the way I try to remember it is if we are moving horizontally, it's backwards. There are more transformations than just the ones we're going to look at in this class. And if you continue on in math, you will learn that almost all of the horizontal things are backwards of what you would expect them to be. So if we are replacing the x with x minus 4, then that's going to move us to the right by 4. We can also reflect the graph. So that involves negative signs. So if we have our function f of x, which I have the equation listed here, then we put a negative out front of the whole function. then that negative is not attached directly to the x. So I think of it as attached to the y. We are going to flip or reflect in the y direction. So we're taking this and flipping it in the y direction, which is over the x-axis. So if we flip this graph over the x-axis, flipping in the y direction, we get a graph. Whereas instead, if we put a negative directly on the x, so we get f of negative x, that's going to reflect us in the x direction over the y-axis. So you can see that this graph flips over the y-axis, kind of like you're reading a book. And we get that reflection. So I know that's throwing a lot at you, but putting some examples to it will probably help. Given the function f of x equals x to the fourth power, find the function that is the result of a downward shift of 3, a shift left of 6, and a reflection about the x-axis. So we have a downward shift of 3, which means we need to go -3 in the y direction. Actually, let's just do a downward arrow 3. Shift left of 6, and then a reflection about the x-axis. The x-axis is the horizontal one, so if we want to flip over it, we are flipping in the y direction. So we need to put our negative with the y. So what this is going to look like is, I'm going to kind of do this piece by piece. Horizontal stuff is just the shift left of 6. So instead of just having an x, I need to take that x and shift left 6. But horizontal's backwards, so instead of using a -6, I need to use a +6. So I'm taking that function, putting a +6 on it, and that's raised to the fourth power. So I just replaced my x with an x plus 6. That's what shifts it left. A downward shift of 3 means I need a -3, not attached to the x, but just sitting back. And then to reflect it about the x-axis, we need to put the negative in front of the y, which is really just out front of the whole thing. Because it's not directly in front of the x, it's out front. If it's easier for you to think about it this way, we can look at just the function notation. So we're taking the x value, we want to shift it left 6, so we want to add 6 to it. We want to downward shift the entire function 3, which is the -3 out back. And the reflection about the x-axis means put the negative out front. And you might be able to see a little bit better now how these two are related. So our function f, we're going to put an x plus 6 in the place where x is. We're going to have a negative out front of that, and there's going to be a -3 out back. Let's see if we can kind of dissect it the other way. If we have the function p, which is equal to r of z, which is -square root of z minus 2 plus 3, it's a transformation on the equation t of z equals the square root of z. Determine the transformations imposed on t. So what transformations are we doing to this to get the graph of p? So we need to identify kind of what's different, what has changed. So we had the square root of z, now we're subtracting 2 from the z, a negative out front, and we have a +3 out back. So having the negative out front, that means we're flipping in the y direction, so we're flipping this way. So we're reflecting vertically. This -2 is attached directly to the z, and z is where x normally is. So we're moving in the x direction, so horizontally. If we're moving horizontally, this -2, you would think to the left 2, but it's horizontal, so it's backwards. So this is going to move us to the right 2. And then the plus 3 out back is our vertical movement, which moves us up 3. Now, a little bit tricky about this one is we're not talking about x, y. We're using different variables. In place of where we normally see x is z. Where we normally see y is this p. So I need to make sure I'm using the right variables here. So if we are reflecting vertically, we're reflecting over the x-axis. Well, we're not reflecting over the x-axis, we're reflecting over the z-axis. So we are reflecting about the z-axis. We are shifting right 2 units and up 3 units. We're going to continue talking about graphs. We're going to first talk about increasing, decreasing, and constant. So we're going to read graphs from left to right, just like we would read a book. So as we move from left to right, if your graph is going up, then it's increasing. As you're moving from left to right, if it's going down, then it's decreasing. And then constant means you're not going up or down, so you're sitting horizontal. So here we have a graph, and we want to figure out when are we increasing and when are we decreasing. So from the very start, we're increasing, 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 increasing until we get here, and then we start decreasing. So the way we write the interval for which we're increasing is, what are the x values that we're increasing for? We're going to assume this graph has arrows because it looks like it should. And we are increasing from negative infinity until we get to this point, which has an x value of -2. Now at this point where x equals -2, we're not increasing because we're not going up at this point. We're not decreasing because we're not going down at this point. We're not constant because we're not sitting horizontal at this point. We're not doing anything. We're just sitting at a point. So if we are not increasing at -2, then to make sure it's only parentheses. Because at -2, we're just sitting at a point. After -2, we're decreasing. So from -2 to positive infinity, we will be decreasing. We're going to bring back that piecewise function that we looked at earlier and see if we can figure out where it's increasing, decreasing, and constant. So working from left to right, we are decreasing from negative infinity until we get to this point, which is x equals 0. So negative infinity to 0, we are decreasing. Then from 0 to 1, we're increasing. So from 0 to 1. You will be tempted to use a square bracket because we have a closed circle, but at the point where x equals 1, just at that dot, you're not increasing, you're not decreasing, you're not constant, you're sitting at a dot. From 1 to 2, we're on this horizontal line, so that's going to be constant. And then from 2 to infinity, we're increasing again. So we need to include that on the list of increasing. And the way we put these two intervals together is with OR, which we use a union for. Absolute extrema is going to be this idea that we carry through to the next unit. And the absolute maximum is going to be the highest point on your graph. The absolute minimum is going to be the lowest point on the graph. They might be at the endpoints, they might not be. So our absolute max, the very, very highest we go, is this point. So that has an x value of 2 and a y value of 4. Our absolute minimum, the lowest we ever go, is this point here, Well, this one has actually really weird coordinates because if you look at the scale, let's zoom in for a minute. This is 2, which makes this one 1, which makes this 1/2. So our x value is 1/2. Then I need to do the same on my y scale. This one's 1. So that makes this one 1/2, geez. But I'm halfway between 1/2 and 2, which makes that 1 3/4, or 1.75. So our absolute minimum is going to be at 1/2, comma 1 3/4. You can use fractions, you can use decimals, it doesn't matter. As long as you understand this idea of the absolute extrema are the absolute highest and the absolute lowest points. Now we use absolute because you can also have relative extrema, which just mean you're higher than the points around you or you're lower than the points around you. So if you look, for example, at this, we're at the top of a hill. We're above the points near us. So this is a relative maximum. This relative maximum has a value, a y value of 0, and it happens at the x value of 0. We have a relative minimum right here. The value of that minimum is -2, and it happens at the x value of 1. So relative extrema are in the general area, are you the highest or the lowest? Absolute extrema are, look at the whole graph, are you the highest or the lowest? So kind of wrapping up this unit, we're going to put some application problems together. A truck rental company rents a moving truck for 1 day by charging $39 and 60 cents per mile. Write a linear equation that relates the cost C in dollars of renting the truck to the number X of miles driven. So the cost C, and I'm going to use C of X so I know that I'm using cost as my function and X as my variable, is equal to, I have to figure out which one's my slope and which one's my y-intercept. This word per indicates slope. So this 0.60 is my slope, and that has to be multiplied by my variable. And that should make sense because it's 60 cents per mile times the number of miles driven. Plus we have the flat charge of $39. So if you rent the truck but drive it nowhere, you're still going to pay the $39, even if you drive 0 miles. What is the cost of renting the truck if the truck is driven 110 miles? Well, miles represents X. So we're plugging in 110 for X. So C of 110 is equal to 0.60 times that 110 plus 39. And that is equal to 105. So the cost of renting the truck and driving it 110 miles is $105. How far could the truck be driven if the cost must be less than $150? So this time we're replacing the cost with $150, and we want to know how far we can drive. So we're solving for X. So that 150 is equal to 0.60x plus 39. If I subtract 39 from both sides, we get 111 is equal to 0.60x. And then if I divide both sides by 0.60, we get x is equal to 185. Now I'm going to be really picky about this just because it's important to read your problems carefully. We need the cost to be less than $150. If we drive 185 miles, it will cost exactly $150. So we need to make sure we drive less than this 185 miles. If we travel any distance less than 185 miles, the total cost will be less than $150. All right, last problem. A company is producing very large stuffed animals. The variable cost is $7 per stuffed animal, and the fixed costs are $25,000. They will sell the stuffed animals for $76 each. Let X be the number of stuffed animals produced. Write the total cost C as a function of the number of stuffed animals produced. So cost. Cost, they gave us numbers for cost. So C of X is equal to, I see that per word again, so I know the 7 is going to be my slope. So we'll have 7x plus we have fixed costs. So right up front, we're going to owe $25,000. Revenue, that's the amount of money we take in. Well, we're selling these stuffed animals for $76 each. So our revenue in terms of the number of stuffed animals that we sell is going to be 76 times the number that we sell, X. Then we want a profit function. What profit means is how much money do you make after you take away your costs? Well, profit is equal to the cost, or sorry, the revenue minus the cost. So however much money you make, take away how much you owe for costs. So that means I'm going to take my revenue function, 76x, and I need to subtract the cost function, 7x plus 25,000. If I distribute the negative through, I'll have P of x is equal to 76x minus 7x minus 25,000, which leaves us with 69x minus 25,000 to be our profit function. Finally, we want to find the number of stuffed animals which must be produced to break even. So we want our cost to be equal to our revenue. Or we want our profit to be 0. Those mean the same thing. Because if the revenue equals the cost, then our profit will be 0. So what I want to do is make our profit equal to 0. 69x minus 25,000. I can add the 25,000 over, so we have 25,000 is equal to 69x. And if I divide that out, I get x is roughly equal to 362.31. So we need to produce 362.31 stuffed animals to break even. Well, that doesn't really make sense because we're not going to make 0.31 of a stuffed animal. So what we're going to do is we're going to round up so that we are on the profit side of things rather than the losing money side of things. So if we make 363 stuffed animals, then we will make a small amount of money rather than losing it. And this just puts us at a whole number because a whole number of stuffed animals makes a whole heck of a lot more sense than partial stuffed animals.